Hey guys, welcome back to Chapter 5 and 6, Discrete and Continuous Distributions. In this video, we're going to cover the binomial distribution and the normal distribution. So if you want to follow along, be sure to have the slides out, or you could just follow the video. And I would also have your worksheet out because we're going to refer to that worksheet a bunch. So the binomial experiment. Experiment consists of n trials. Okay, each trial results in either a success or a failure. So that's where the bin in binomial comes from. So it's binary. It's either a yes or a no, a fail or a success. Probability of success is p, and that's constant from trial to trial. So that kind of leads us into point 4, that all the trials are independent. So because that probability from one thing to another doesn't change, then we know that it's that they're n independent trials. Examples of this would be the roulette table at a casino, or rolling dice, like in different trials. So you'd roll a die now. You'd come up with a success or a failure. Success might be rolling a 3. And then you roll a die again. The first roll has no bearing on the second roll. There's no removal or anything like that. Okay, so they're all independent trials. If x is the total number of successes in n trials of a binomial experiment, then x is a binomial random variable. And the probability of obtaining x number of successes in n trials is given by this formula. So this formula looks crazy, right? But it's not as crazy as it looks. Okay, so probability. So first we would write it. So this is our standard probability function p of x, and then this piece of it we've seen before. This was our choose formula. This was n choose r. I think I forget how we denoted it. It was n choose r or n choose r. Like that, or n choose x, or whatever you wanted it to be. Okay, so in this scenario, it is going to be represented as n choose x. So this is something that we learned in our counting rules in Chapter 4, at the tail end of Chapter 4. So think of this formula in 3 parts. Think of it as in this combination, this counting rule combination, this probability of success, and this probability of failure. So P is the probability of success, okay, which we've defined here in number 3, and then Q is the probability of failure, which, because it's binary, is just going to be 1 minus the probability of success. So Q is equal to 1 minus P. So this whole formula shakes out to the probability of the number of successes. So we would assume that all these successes are independent. So say you wanted 2 successes, it would be p times p, or p squared, and then the number of failures. It'd say you have 10 total trials, so you'd have 2 successes and 8 failures. So if there's 10 total trials, n, then you'd have n minus 2. So 10 minus 2 is 8, and that would give you your exponent up here. So it would be the number of successes times the number of failures, and multiply those all together independently, right? And then the number of combinations that those can occur, which is that choose formula, which is the big choose formula here. Okay, so that's how we'll see that. And let's look at this. This is some just graphical representations of the binomial distribution. And you can see how it's labeled here. So binomial when n is equal to 5 and p is equal to 0.1. And then this is the function actually graphed. So that's how that looks. But one thing that you'll notice is that as n gets large, it has a tendency to look more and more like a normal curve. And we can see that by the fifth one here. If we have 1, 2, 3, 4, 5, this bottom middle one. So that's just something to think about. I'm not sure we're ever going to have you graph any of this stuff, but just a good graphic to have. And then here are the formulas. So I think I said this in the last video, that these discrete random variables, we have that original formula that we used for the discrete random variable, which was the big summation formula. We had the, for the mean, we had the summation for all x of x times p of x. And then for the variance, I think it was the summation for all x of x minus mu squared times p of x. And, that's a whole big summation. The great thing about these named distributions is that some mathematician has already solved these formulas for you, and we've got formulas that are really, really, really easy to determine what the mean, standard deviation, variance is, and so on and so forth. So the great thing is look here, for the binomial random variable, mu of x is just going to be n times p, and the variance is going to be n times p times q, and then the standard deviation, as always, is going to be the square root of the variance, so the square root of n times p times q. All right, go ahead and turn to number 3 in your worksheet, and we'll go ahead and get started on those problems. Suppose that x is a binomial random variable with n equal 5, p equal 0.3, and q equal 0.7. Write a binomial formula for this situation and list the possible values of x. Well, first of all, we know that the possible values of x, here I'll just put a here, possible values of x are going to be contained from 0, 1, 2, 3, 4, and 5. We know that just because n is equal to 5. So remember there are n trials, and x is going to be the number of successes. Right? So we have 0.3. We have 0.3 probability of success in any one of the trials. So you could get all of the trials as a success. That would be 5. All except 1, that would be 4. All except 2, that'd be 3, and so on and so forth. Or just no successes, all failures, which would be 0. So those are the possible x values. And then it's asking for what the binomial formula is. So the binomial formula is that p of x is equal to the n choose x. I'm not going to write out the crazy formula, the n factorial over x factorial times n minus x factorial. But so we can just represent that as n choose x, and that's going to be times the p, the probability of success, to the number of successes, times q, the probability of failure, to the number of failures. So that would just be total number of trials minus the number of successes. N being the total number of trials, x being the number of successes. So that's just going to be the number of failures, okay? And in our case, we just kind of plug in some numbers. It's going to be p of x is equal to 5 choose x of let me erase that. Of 0.3 to the x. So let me 0.3 to the x times 0.7 to the 5 minus x. And that's our function. That's our probability function. So b, for each value of x, calculate p of x and graph the binomial distribution. Don't worry about graphing it. I forgot to take that out. I don't really feel like graphing it, do you? So we won't worry about it. So for each value of x, calculate p of x. So this is going to be A fairly intensive calculation. So we're going to go through all of these. So there's 6 different values, 0 to 5, and we're going to run them through this formula to get we're going to get our p of x. Okay. And so I'll just start this over here. We'll say p of 0 is equal to 5, choose 0, times 0.3 to the 0th times 0.7 to the 5 minus 0. So it's just going to be 0.7 to the 5th. And 5 choose 0, so here's a rule that you should know. Anything choose 0, there's only going to be one way to do it. Okay, so that's going to be 1 times 0.3 to the 0th. So anything to the 0th is actually equal to 1 as well. So 1 times 1, and then 0.7 to the 5th. If we calculate 0.7 to the 5th, we get 0.1681. So then the whole thing is just equal to 0.1681. Okay, so we're just going to do this for all of them. Don't worry, this is not something that you're going to have to do in every binomial problem that you do, but for this example, I'm just going to show you guys how to do it. So 5 choose 1, this one's going to be 5 choose 2, it's going to be 5 choose 3, 5 choose 4, 5 choose 5. So at this point, I would expect you guys to do this choose thing in your calculator. You don't need to like run through the whole crazy calculation on your own. I'd want to see on a test, like if you're doing a problem specifically about combinations, to do the calculation by hand and show that work. But I would certainly expect you to check your work via calculator, via Excel, or whatever. And this class is obviously going to be a little bit different because you're going to be taking your tests online. So I'm obviously going to expect a fair amount of detail from you guys in order to show me that you really understand what's going on. So that's that. So I'm going to do all these. 0.3 to the 1. Uh-oh. Well, that's a 7 out of 4. So this is, I'm just going to shorten this. So this is going to be 5 minus 1, so 4. 3 to the 2. And when we go ahead and calculate all these out, we're going to get 3602, 0.3087, okay, so what we see here is not surprising, right? So we say that in one of these trials, we have a probability of success of 0.3. So it's not a favorite. It's not a favorite to come through. It's not, you're not likely to succeed. You're only about 30% to succeed. So they're pretty much telling us that if you wanted, the likelihood of succeeding 5 times in a row, right? So x equaled 5, the probability of x equal 5 is 0.0024. And this makes a lot of sense. So we assume that these are independent trials. So the only way for this to occur is one way, right? 5 choose 5. That ends up being a 1. and we have no failures, so this ends up being a 1 as well, and 0.3 to the 5, so they're all independent trials, so it's 0.3 times 0.3 times 0.3 times 0.3 times 0.3, and that's all going to equal out to that. So not surprising that something that you're a significant underdog to have a success in, that you'd be a very significant underdog to have 5 successes in a row. And so that's what that means. Okay, so we've calculated the possible probabilities for each different x value. So I'm just going to write these over here. As always, I'm going to show you guys multiple ways to do a lot of this stuff. So I guess first thing, let's use the table. Okay, so in the back of your book, there's a table that I believe is on page 599. So that's back in the appendix, for which you can get these values as well. So I'm going to go ahead and pull it up. I've also put it on Springboard for you. It's also going to be, or it's also in the ebook. So you have multiple ways to come by this table. So yeah, let's look at this. So we go, I guess it's not 599. No, I thought it was 599. Maybe not. Well, look for the table. You'll find it. Okay. So we're looking at the binomial table. This is saying page 631. I could have sworn it was 599, so we'll see. But so there's a bunch of different binomial tables here. So first thing that we want to look for is what our n value is. Back on the other worksheet, we had n equal to 5, right? So there's n trials. So there's 5 trials in this case. So we look over here and we find n equal to 5. Okay? So boom, right there. Then we want to look and find, well, what is the p-value that we're using? What's the probability of success? So we go back here. We had a p-value of 0.3. So we go back here. So we're at n equal 5. We're at 0.3. And then now we can look up all the values here to see, we look up all the values to see if they match what we came up with. So these are going to be the p-values of all the different x values. So x equals 0, 1, 2, 3, 4, 5. And then look at these p-values. Oops. Look at the p-values here. 0.681. That matches what we got. 0.3602 and 0.3087. Yes. 0.1323, 0.0284, and 0.0024. And that's exactly what we had down here. So that's an easy way to do it. That's a way that you don't have to run through a laundry list of calculations to do. So that's how I would expect you guys to go about using or go about doing it on the homework. I guess I'll show you another way to do it. You can also use Excel. So for Excel, I set up just some columns here. And I put in a column. I made a column for my x value. I made a column for my number of trials n, for my p-value. And then I just put this column in for cumulative. Basically, when you do the Excel formula, it's going to ask you, do you want to know the probability of that value or the probability all the way up to that value? And that'll become more apparent how we're going to use it here in a second. But for right now, we'll leave it as a 0, because 0 is just going to say we just want the value. We just want the probability of that value. And so the function is binom.dist, and then it's asking for the number s. So that looks like that's just going to be our x value. So we would click on that cell. And then the number of trials, n, so that cell. And then the probability of success. So number s means number of successes. And then probability s is the probability of success. And yes or no to cumulative, it's saying true or false. something to note in Excel. For true, you can just put a 1, and for false, you can put a 0. So that works as well, other than true and false. So we close that off. And so this is now going to tell us the probability of success, or the probability of exactly 3 successes out of 5 trials. So we have n equal 5, so 5 trials with a probability of 0.3 for a success on any trial. And we want to know, well, what's the probability of any success here? So, or the probability of 3 successes specifically. So it's telling us that it's 0.323. If we go back to our sheet, P of 3 all the way over 0.1323. We could change that and say, well, what about when x is equal to 5? 0.00243. 0.0024, and I just cut it off at 4 digits. So yeah, so it's dead on. So there's that. And then lastly, I'll show you another way to do it. So we've done the hand calculation, we've done the Excel calculation, we've done the table, and now I'll just show you how to do it in Megastat. Obviously, I don't want you guys to use all of these methods. Just use whichever makes sense in the situation. It's probably going to make sense to just go look it up on the table, because then you don't got to run any calculations, and that's probably easier for everybody. But in case maybe the values aren't on the tables, or whatever it is, you have options. But yeah, I just wanted to show you in Megastat. And so in Megastat, we would just go to Megastat, probability, all the way. Oh, I just realized you guys can't see that. Ah, very nice. Okay. Go to Megastat, probability, discrete probability distributions, and then you would put in the number of trials. So looks like I've already done this, 5, and then just the p-value. And it's actually going to run it for all of the x values. So we hit OK, puts it into an output sheet, n equal 5, p equal 0.3, and then look. For x0, gives us the p of x right there. These numbers look really familiar. Cool. All right, and then this has the cumulative probability. So it's just adding up the probability summed to that point. And as we get to the last value, obviously the sum is going to be equal to 1, because that's our total probability. All right, so now it's asking us to find some of these individual probabilities, or these cumulative probabilities. And we've done some of this already, but we're going to go ahead and walk through it anyways. So C says find probability of x equal to 3. Okay, that's super easy because we've calculated almost everything out already. So we'll say C, probability of x equal 3 without calculating anything, because we already did. We know the probability of x equal 3, and that is 0.1323. And then D is asking for the probability of x less than or equal to 3. Probability of x less than or equal to 3. And that's just going to be adding up the probability. So here we go. We'd say that this would essentially be equal to the probability of x equals 0, probability of x equal 1, plus the probability of x equal 2, plus the probability of x equal 3. So we just add all those up, which we have over here, and we are going to get 0.9692. Then E asks us the probability of x less than 3, not less than or equal to 3. So this would just be the probability of x equals 0 plus the probability of x equal 1 plus the probability of x equal 2, not including x equal 3. And so then we just add those up, and those are going to add to 0.8369. then F is going to ask us what is the probability of x greater than or equal to 4. And this is something important to note. If we're looking at these x values here on the left-hand side, the 0, 1, 2, 3, 4, less than or equal to 3 is going to be the exact opposite of greater than or equal to 4. Right, so if we're counting less than or equal to 3, that's going to be, we're counting 0, 1, 2, and 3. And if we were counting greater than or equal to 4, that would just be 4 and 5 that we're looking at. So we would just be adding those up. So it would be, we could add up the probability of x equal 4 plus the probability of x equal 5. Or we could just say, well, we know this is the total probability of 1 minus the probability of anything less than 4, which happens to be x is less than or equal to 3. And we only do that because we've already calculated that number. So that would be 1 minus 0.9692, or 0.0308. Move on to G. And G is probability of x greater than 2. And that just would be, it could just be 1 minus the probability of x equals 0 minus the probability of x equal 1. And that's just going to be everything, and minus the probability of x equal 2, right? Because it's just strictly greater than. And that's just going to be 1 minus 0.1681 minus 0.3602 minus 0.3087. And that would all shake out to be I don't see it on my sheet. 0.1631. Okay, and then now looks like H is just going to ask us to calculate the mean, median, and mode. And the mean, we have a nice simple formula, and that's just n times p, which is just going to be 5 times 0.3. This pen is driving me nuts. I don't know why it randomly decides to erase stuff. And variance is going to be, n times p times q, which is 5 times 0.3 times 0.7, which is equal to 1.05. And then standard deviation is just going to be the square root of that. Running out of room here. And that is going to be 1.025. And I guess because I ran out of room, a decent sized part of the problem. Okay, so on to I. I wants us to calculate the interval of mu of x plus or minus 2 standard deviations. And for us, that's just going to be is our mu? Our mu is 1.5 plus or minus 1.025, or so 2 times 1.025. So that's going to equal a range of sorts. So on the high end, that's going to give us 3.55. On the low end, it's going to give us minus 55, I believe. Minus 0.55. And now it wants us to find the probability that x will be in the interval. Okay, so now because we have a discrete function, we have to figure out, well, how many x's are in this interval. So we kind of just count up the x's that are in the interval, and then we add up their probabilities. So the x's that are in the interval, so I'll just say x's in the interval would be, what would they be? They would be 0, 1, 2, 3, but not more than 3, right? Because 4 is not in this interval and 5 is not in this interval. So really it's just asking us, well, what's the probability that x is less than or equal to 3? I think we already did that, right? So that's up top here. Probability that x is less than or equal to 3. We calculated that out to be 0.9692. So that's that. Okay, so that was binomial. I know that probably feels like a lot, but go ahead and do some practice problems. Go ahead and skip to the review portion of this worksheet if you want, and then try some problems on your own. Lean on that formula. Use your resources. Use the book. Use the review. Yeah, use whatever you need to use. And just re-go over the video. All right, but we are going to move on now from binomial to, it looks like I already showed you how to use this table. This is just a snapshot of the binomial table. And onto the normal distribution. So if you thought that that last formula was scary, to me this is like just bonkers. You have sigma in there, you have pi in there somehow, you have e, you have x and mu, and then sigma again. So not really sure why they put this in here. I mean, this is certainly the function. This is certainly what the normal distribution's probability density function is. This is the last time you'll see it. I'm not quizzing you on this. I'm not testing you on this. You're gonna, in this class, the main thing is you need to learn how to use the normal distribution, okay? Not use the function. So we're going to be calculating z-values. We're going to be calculating probabilities from the standard normal curve. And we're going to be doing all sorts of stuff with the normal distribution, but you will not need to know this formula, okay? So yeah, take a look at it and then just forget it. All right, so on to the normal curve. Everybody sort of has some prior experience with the normal curve, but we'll go ahead and get to it. Probabilities of the normal curve. There are an infinite number of normal curves. The shape of any individual normal curve depends on its specific mean and standard deviation. Okay, so when we work with the standard normal curve assumes that the mean is 0 and that the standard deviation is 1. So that's why we use z-values. We'll get into the z values in a little bit, but this is to say that if we assume something is a normal distribution, it's allowed to have whatever mean it needs to have, and then associatedly whatever standard deviation it needs to have. But when we calculate a z value, we call that normalizing the curve or standardizing the curve, or standardizing the value, and that's going to bring it back to the normal, the standard normal curve, which makes it a lot easier for us to find probabilities. It makes it so that you don't actually have to go to that crazy formula and figure out the probabilities based upon that. Okay, so we'll be standardizing it, and that's that. The highest point is over the mean, which is also the mean, median, or the mean and the mode. We actually saw this in, I believe, chapter 3. This was the graph that showed us the curves, and then you saw like mean, median, and mode in the symmetrical curve, and then you saw mean, median, and mode and what order it was in on curves that were skewed left or right. But so this normal distribution, the normal curve, is perfectly symmetrical, and the mean, median, and mode are all centered about the mean. They're all right in the middle there. Then we just talked about its symmetry. The tails extend off into infinity in both directions, and the area under the curve to the right equals the area under the curve to the left because it's perfectly symmetrical, and then each half has 0.5, which makes sense because then it means that the total probability is 1 of the whole thing. Okay. This is just talking about the position of the curves. The higher the mean is, then there's shifting that occurs. And then the taller a curve is going to have a smaller standard deviation. The wider a curve is going to have a larger standard deviation, which makes sense. So if you think large standard deviation, that means that there's higher variance. That means that there's a higher spread of data. That's going to be a flatter curve with much a wider range of data. Okay, so this is going to be how we find probabilities with the normal curve. We're looking at an interval. So this is something we described when we were looking at the uniform distribution, which was another continuous one. So we have an interval from A to B. So this interval, this is the probability that X is between A and B. So this is just the visual representation of that. And here's just another slide that shows us that empirical rule, the plus or minus 1 standard deviation, 68% is going to be in there, plus or minus 2 standard deviations, 95%, and then plus or minus 3, 99.73. And then lastly, this is going to take us to the worksheet. But yeah, this is what a normal curve would look like with a mean of something that we either know or calculate, and a standard deviation of something that we either know or calculate. And then this is showing the translation down into the standard normal curve. Okay, so we're going to use a z-score in order to turn something into the standard normal curve, because then we're going to be able to just go look up values in the back of the book and be able to determine probabilities. So we're going to get some practice in with just calculating z-scores. It's a very simple thing. As you can see by the formula, z is just equal to x, so minus mu over the standard deviation. So without any further ado, let's go to the worksheet. Okay, so we're going to look at number 4, and it's just asking us to calculate the z-scores based upon these x values. So we'll start with A. So z is equal to 25 minus mu of 30 all over a standard deviation of 5 which is a negative 5 over 5, which is negative 1. 2 is z is equal to 15 minus 30 over 5. Notice how the mu and the standard deviation don't change. It's just the x value that are changing in these. You get negative 15 over 5, which is negative 3. Z is going to be 30 minus 30 over 5, which is 0 over 5, which is 0. So that would actually mean that x is the mean. X is mu, which we can see is the case, right? X is 30, mu is 30, because there's no deviation there. Z is equal to 40 minus 30 all over 5, which is 10 over 5, which is 2. It's a positive 2. And for E, Z is equal to 50 minus 30 over 5, which is 20 over 5, which is 4. Okay? So that's the case. So that's that. That's how you calculate z-scores. It's that easy. Now, the numbers aren't always going to be as perfectly round and easy to work with as they are right now, but that's the concept. It's just z is equal to x minus mu over the standard deviation. So what we're doing is we're normalizing. So we're taking that value of 50 and we're just making it, or we're turning it into z equal to 4, which is to say that it is 4 standard deviations above the mean. Say z was equal to negative 4, that would be 4 standard deviations below the mean. Okay, so that's just a point on the standard normal curve. So I'll go back here. This is just a shot of the table, and we're going to use this in a little bit. And these are just pictures of calculating the probabilities. So let me get us to, let's just start working on problems. You guys can go back and look at these slides as you would like, but the video is running a little bit long, so I'd rather just get into problems. So this is this part, number 5, is not about calculating z's. So this is assuming that we know z values, or we're given z values, or whatever. This is about using those z values. So I'm going to do a few of these, and then I'll let you guys do the rest of them, because there are a lot here, and I don't think we need to do 9 of them. Okay, so A is saying find the probability of 0 is less than z is less than 1.5. And so all that's saying is what's the probability that z falls between 0 and 1.5. So what I'm going to do first is I'm going to draw a graph of what this is saying. Okay, so this is my best normal curve, sadly. And so because we're working with z means that we're on the standard normal curve. So we know that mu is right here, and that's equal to 0. So then we have 1, 2, 3, negative 1, negative 2, negative 3. Okay, and so now it's asking, well, what is the probability of z being between 0 and 1.5? So let's go find 1.5. And then let's find 0. 0 is right here. So we want to know the probability in this spot right here. Okay, so that's how. So this is how we would visualize this. So this would be the probability from 0 to 1.5 is represented by the area under the curve here. Okay. And so what we do in order to solve for this is we can find what the probability, so we'll say probability of 0 is less than z is less than 1.5. This is just going to be the probability that x is less than 1.5, or sorry, z is less than 1.5, minus the probability that z is less than 0. Okay? Think about that for a second. I'll let you think about that for a second while I draw the next graph. Okay? So think about why that might be. So 1, 2, 3, -1, -2, -3, 0. So the idea is that when we use the tables in the back of the book, so we're going to look up z values, and they're going to give us the probabilities that are cumulative. So probabilities from left to right. So it's going to start on the left-hand side, the negative side, and it's going to count up the probability all the way over to the z value. So when we look up z is less than 1.5, so this spot on the graph, when we find that value, it's actually going to give us the area under the curve of this whole thing all the way up until 1.5. Okay, so when we say that, if we're wanting to just find a sliver, so if we're wanting to find this sliver right here, then we'd have to minus off the part of the curve that is from here back. Okay, so then we would find this. So then we would minus off this piece, which would just leave us with this little sliver, which is what we're looking for up here. Okay, so we look for this probability value, and we look for this probability value, and we minus it off. And that's going to leave us this chunk right here. Okay, so we're going to go over to the table, and let me find the normal curve. Okay, so the normal curve looks like it is table A3. So the way that we do this, we're first going to find our first z value. So I believe our first z value was 1.5. And so we scroll down here on the z table, we look for 1.5. Okay, so now which number do we use in this whole thing? That's actually very easy to know. So this column just deals with one decimal place, so 1.50 essentially. So that's going to be these values, so all the way down here. But like say this was 1.51, that would be here. 1.52, that would be right here. 1.53, that would be there. So for just straight 1.5, we just have this value. So our value is 0.9332, so that's probability. So we write that here, 0.9332. Now we're going to be minusing off the probability that z is less than 0. I actually already know what that is, and you'll see why here in a second. But like, let's look at 0. Z is less than 0 is 0.5 exactly. And that makes a lot of sense. This makes sense because we already said that at 0, this is where half the data is over here and half the data is over here. So we know that there's 50% probability on this side. Okay? So we minus these from each other, 0.9332 minus 0.5000 is equal to 0.4332. And that's our answer. So that's the probability that z falls between 0 and 1.5 is 0.4332. Okay? Because this video is running pretty long, I'm only going to do one more. I'll just do B. B seems pretty easy. So we'll do B. Or it doesn't seem pretty easy, but it seems different, which I like. So B is probability that z is greater than or equal to 2. Now, in continuous distributions, greater than or equal to doesn't mean anything. Greater than or equal to is the same as greater than. That's only in continuous distributions, okay? In discrete, that would be something that we'd really need to look out for, but in a continuous, greater than or equal to, they're all the same. So this is easy because in our table, it gives us the cumulative probability. So meaning it's giving us everything up into a certain point. So everything from left to right. Okay? But now this is asking for the probability that something's greater than. So if we were to draw out our normal curve, which I am just awful at. Okay. 1, 2, 3, -1, -2, -3. This is asking for this point right here in the area right there. Okay, we know if we looked up the z-value of 2 in the table, it would give us all the area back this way. Okay, but we need to know this area. So that's easy, right? We know that the total area under the curve is equal to 1, so we could just say, well, okay, then this is just going to be 1 minus the probability that z is less than 2, which is the value that we can look up in the table. So that's equal to 1 minus, and then we go to the table, we find 2, and that's 0.9772 right here. We go back. And that gives us 0.228. That's that. All right, guys, if you guys have any questions on this, please let me know in the discussion forums. If you need to see more examples, I can write some up. Actually, what I'll do is I will just put up my version of this as a PDF, and I think that'll be helpful. I just think it'll be a big time waster if I'm just sitting here walking through these on video. But be sure to ask questions. And yeah, I'll be sure to focus on this a little bit more in the review, but just wanted to get through some of these. Thanks so much, guys, and next time we will cover Poisson and exponential.